let's continue the study on reaction kinetics. In fact, in the last session, I explained about the collision theory, and we had a discussion on the three factors of the collision theory and how the four factors which affects the rate, which is temperature, pressure or concentration, the particle size, and catalyst. These four factors, how it affects the rate, was explained using collision theory. The collision theory talks about the importance of the frequency of the collisions and the energy of the colliding molecules. Colliding molecules should possess energy greater than the activation energy. And also we discussed about the importance of the correct orientation of the atoms during a reaction. Right, so that was discussed in detail, and we also had a discussion about the catalyst, a substance which increases the rate of reaction without being used up in the reaction, and catalyst increases the rate of reaction by providing an alternative route with lowered activation energy. Then we discussed about the different types of catalysts, the homogeneous and the heterogeneous catalysts, and how catalyst is regenerated at the end of the reaction. Our last discussion was about the lock and key model and the specificity of the biological catalysts, the enzymes. I think there where we stopped last. As for the advantages of using catalysts, catalysts will decrease the energy demand for a reaction. It will also increase the percentage yield, and then atom economy will be increased by using a catalyst, right? So because catalyst increases the rate of reaction, it's more profitable, right? To get more products at a lesser time. So let's carry out few experiments to prove how the four factors, the temperature, pressure, concentration, the particle size, and the catalyst increases the rate of reaction. We'll begin with the effect on catalyst on the reaction rate. So we'll take this particular reaction, the decomposition of hydrogen peroxide to water and oxygen. Now, hydrogen peroxide, in the presence of sunlight, it will decompose to water and oxygen gas. Water and oxygen gas. Now, this reaction is a decomposition reaction, and this occurs in the presence of light. So that's the reason the hydrogen peroxide is often stored in amber bottles, dark bottles, amber bottles, because it decomposes in the presence of the light energy. Now, let's see, our goal is to prove that the catalyst increases the rate of reaction. This is an extremely slow process, and the rate of this process is speeded up by the use of manganese dioxide catalyst. Right, so what I'm going to do is I'm going to collect the gas in a graduated gas syringe. You can see oxygen gas is produced. So I can collect the gas in a graduated gas syringe and record the time and record the volume of the gas collected at regular time intervals. And then you plot a graph of the time versus volume of oxygen produced. The gradient of the plot will give you the rate of reaction. The thing is, you have to carry out the reaction twice. Once in the presence of catalyst and then in the absence of catalyst. So we'll notice when in the absence of catalyst, it takes a longer period of time for the reaction to complete than in the presence of catalyst. So that shows the catalyst increases the rate of reaction. Of course, certain conditions should be kept constant, like the concentration of the hydrogen peroxide solution should be kept constant, the volume of the hydrogen peroxide should be kept constant, and then the surface area of the manganese dioxide catalyst, because if you increase the surface area, that becomes a more effective catalyst that will also increase the rate of reaction. So we have to make sure that same surface area, if you're using powdered manganese dioxide, both you have to use the same manganese dioxide. So this is the apparatus set up for the experiment. You have, this is the hydrogen peroxide. You can collect the gas in a graduated gas syringe. As oxygen gas is collected, the plunger gets pushed away from the syringe away from the 0 mark, and you record the volume of gas produced at regular time intervals. This is hydrogen peroxide, and this is the graduated syringe, and you plot a graph. This is volume of oxygen versus time. You'd first do without the catalyst. You see a very slow process. Reaction stops at at a greater time. It takes a long time for the reaction to complete. This is without manganese dioxide. And then you repeat the experiment. Again, the same amount of hydrogen peroxide, same concentration. This time you add some solid manganese dioxide catalyst. And then you will notice the reaction ends at a lesser time. Right, it takes only lesser time for the reaction to end. This is with manganese dioxide catalyst. So that shows the catalyst increases the rate of reaction. Right? Is that clear? So we can prove that the manganese dioxide is a catalyst by weighing the catalyst before we start the experiment. You weigh the catalyst, record the mass, and at the end of the experiment, you filter off the catalyst, dry it, and then you reweigh it. That will be almost the same mass. So that shows that manganese dioxide is not a reactant, but it's a catalyst. Can we also use powdered manganese? Yeah, we use powdered manganese dioxide. We can use powdered manganese dioxide. Yes. The rate can be measured by collecting oxygen gas produced in a graduated gas syringe. The decomposition is very slow under normal conditions. Addition of the catalyst manganese dioxide will speed up the reaction, producing oxygen gas at a higher rate. Carry out the reaction twice, once without the catalyst and then with the catalyst. Record the volume of gas at regular time intervals. Plot a graph for time versus volume of oxygen produced. The gradient of the plot will give us the rate of reaction at each experiment. Please copy this. Copy the reaction apparatus and the graph. What I have written here on the graph is with manganese dioxide, without manganese dioxide. The method of the experimental method is determined by the type of reaction. Now, this is a reaction where oxygen gas is produced. So if a gas is produced, always we can use this method. You can collect the gas in a graduated gas syringe and record the volume of gas at regular time intervals. Okay. This question, we only can use manganese dioxide as a catalyst. Yes, there are other catalysts also, but manganese dioxide is the best catalyst for this particular reaction. I hope all have copied. Anyone needs more time, let me know. Describe the experiment to show the rate dependence on the concentration of the reactants. Now, as the concentration of the reactants increase, the rate of reaction also increases. So we can do this by magnesium reacting with hydrochloric acid. Right, magnesium reacting with hydrochloric acid. We can use hydrochloric acid of two different concentration. We know magnesium reacting with hydrochloric acid gives magnesium chloride and hydrogen gas. So as a gas is produced during the reaction, we can also still use the same apparatus setup because the gas is produced, right? So the reaction is this: magnesium, hydrochloric, magnesium chloride, and hydrogen gas. So carry out the reaction twice, once with a lower concentration of hydrochloric, and then with a higher concentration of hydrochloric. And like before, you record the volume of gas at regular time intervals. You will notice with a higher concentration, you get a greater gradient. The reaction comes in at a lesser time, which means the rate of the reaction is increased with increased concentration, because we know the reason. As the concentration increases, the number of particles, number of molecules in a given unit volume increases. So when that is increased, what happens? The frequency of the collision, that's the effective collisions per second, or the frequency of the collisions increases. As the frequency of the collisions increase, the rate of reaction increases, right? So that you have to carry out the reaction twice with the. You can use 0.1 m HCl and then 0.5 m HCl, right? And you have to ensure that the magnesium is the same amount of magnesium we use and the same surface area of magnesium. We should not change the surface area of magnesium. The same surface area should be used, right? So I'm going to just alter the same diagram for the next one. So this is the volume of hydrogen gas. This is 0.5 m HCl, 0.1 m HCl, and this is the magnesium. So this is hydrogen gas which is collected. So carry out the reaction twice, once with higher concentration and again with lower concentration. You can copy this. For the next question, question 16, carry out the reaction between constant mass of excess magnesium metal. We use excess magnesium to ensure that all of the hydrochloric reacts. Constant volume of two different concentrations of hydrochloric acid. Each time carry out the experiment with one concentration. Record the volume of hydrogen gas liberated at regular time intervals. Plot a graph for the time versus volume of hydrogen produced. The gradient of the plot will give the rate of the reaction at each experiment. You can copy this reaction, the apparatus, and the graph. This is the hydrogen gas. The volume of the gases produced in both experiments may not be the same. So I have just drawn as it's the same, but volume will differ because the hydrochloric moles is a limiting reagent here. So that hydrochloric moles differ, the volume will not be the same level. Anyway, the gradient will differ. Please copy this. Right, so that's how we prove increase concentration increases the rate of reaction. The question is, what can we conclude from the above reaction? You can say concentration is directly proportional to the rate, or you can say increased concentration increases the rate of reaction. Concentration of the reactants, okay, say rate is directly proportional to the concentration of the reactants. Rate is directly proportional to the concentration of the reactants. Next experiment. So we studied so far how the concentration and the catalyst affects the rate. The third is the surface area. For this, we can use this particular reaction, solid reaction, which involves a solid, which is calcium carbonate reacting with hydrochloric acid. This reaction produces calcium chloride, carbon dioxide plus water. So you have to carry out the reaction twice, once with larger particles of calcium carbonate, and the second experiment with tiny particles or smaller powdered particles of calcium carbonate. When you powder it, the surface area increases. And in both experiments, we have to maintain the same volume, same concentration of hydrochloric acid. Now, when you look at the equation, you can see again the gas is produced. So you can collect the gas in a gas syringe and do the experiment. But for a change, I'm going to use a different method because we use the same method twice. So what I'm going to do is I'm going to record the decrease in mass, a different method of measuring the rate, right? Because as carbon dioxide gas is given off, the mass of the reactants will decrease. Mass of the reactants will decrease. So you have here